and neutrons in particular in an atom. If we can figure out the number of electrons with the symbol, great. However, nuclear chemistry is referring to the nucleus. So our focus now is the nucleus, kind of the identity of an atom, the insides, not the outsides, which is the electrons and how it bonds. So on that worksheet, I give you 8,3Li+. And then you can see there's a list of things, the atomic mass, atomic number, protons, electrons, neutrons, that we have to figure out. So again, if I'm looking at the sheet that was titled Symbols and Atomic Structure, number 1 on that gives you 8,3Li+. Recall that the top number of this symbol is the mass number. So on that sheet, how about we write an 8 in that first entry for the mass number, the atomic mass. The bottom number of this symbol, the 3, is the atomic number. It matches up with what's on the periodic table. Recall again, the elements are arranged by atomic number on the periodic table. Also recall, the atomic number is the same as the number of protons. So if you know the atomic number on the periodic table, you know the number of protons, which is 3 for this one. Now again, it isn't a big point of emphasis this week, but hopefully we can still determine the number of electrons something has. If you have a +1 charge and 3 positive protons, how many negative electrons do you have? 2, right? 2 negatives, 3 positives gives you a +1 charge overall. Lastly, what we do need to know today is not only how to identify the number of protons, which is the atomic number, but the neutrons we have to know as well. And recall, protons plus neutrons equals the mass. It's a mass of 8, and I have 3 protons. I have how many? 5 neutrons. So this is something that we went over first semester, but we need to know again today. So how about you kind of on your own, almost kind of a warm-up now, try to fill in as much of that worksheet as you can. We'll go over the answers in a couple of minutes, and then we'll get ready to start showing why we need to know the numbers of protons and neutrons. Okay, so again, what we have to go over today is that within the nucleus of an atom, there's 2 kind of conflicting forces occurring. And if one is stronger than the other, it determines whether or not a nucleus will be stable and will hold together, or will be unstable and will go through a nuclear reaction. First off, the first force we have to talk about is called repulsion, or the repulsive force. Our textbook might refer to as the electrostatic force. We usually like to use repulsion because that term is something that students are familiar with. We know what it means to repel. Well, think about it. In a nucleus, unless you're hydrogen, you have more than 1 positive proton. And if you have more than 1 of the same positively charged species in a small area, they are going to repel each other. That's what the repulsive force is. And if they repel each other too much, it's going to rip the nucleus apart. That changes the element. The element's identity is its number of protons. We just went over that. Atomic number is the same as the number of protons. So if your element breaks apart, and now all of a sudden instead of having 40 protons, it breaks into 2 things, and one has 35 and the other has 5. Well, now it's 2 different elements. That's a nuclear reaction. Just like a chemical reaction is when elements change partners and they make new compounds, we can make new elements with this type of process. The thing about the repulsive force is it acts over a large distance. Do we have any Cubs fans in here? Oh, good. Now I can pick on you. I can't stand Cubs fans, Noah Dixon. My hatred of them isn't just because you're in the room with me right now. When you leave this room, I still can't stand you because you're a Cubs fan. There's other parts of you that aren't that bad, but since I now know that you're a Cubs fan, it's really changed my opinion of you. After a staff meeting, I saw Mr. Kolpak walking out. He's talking to Miss Ryan, and they're bragging about the Cubs winning by, and I just, why? Why do perfectly good people have to like the Cubs? Now that makes me repulsed by you. And that repulsion doesn't matter if we're in the same room or if we're miles apart. Because, oh, you're a Cubs fan. I don't like it one bit. Two protons, it doesn't matter if they're right next to each other or if there's a little space between them. They're still two positively charged things, and they're going to repel and pull away from each other. So first off, I wanted to lead with what's trying to tear the nucleus apart. It's these protons trying to repel. Well, there's one other thing that's inside of a nucleus. It's the neutrons. So they must be the thing that's trying to hold it all together. The neutrons have a lot of roles. First role, kind of simple, they get in between the protons. So instead of me being right next to Dixon and my hatred for the Cubs and his love of the Cubs now affecting us, I can have Jackson in between the two of us. He can be like, okay, guys, it's all right, don't worry about it. They're both decent baseball teams, you know, NL Central, yay, we should all cheer for each other type thing. So he's kind of the guy in the middle. You know, there's a fight in the hallway, there's someone gets in the middle, and it's knock it off, knock it off. They're trying to cool everything down. There's only one element on the periodic table that doesn't have neutrons in its nucleus. Hydrogen. Hydrogen doesn't need neutrons because it's only one proton. There's nothing else for it to repel against. So the neutrons, kind of that, cool it guys, let's calm down. What you're going to learn on my next slide is the second type of force besides repulsion, and this was on the reading guide. It's called the strong nuclear force. Now, some texts call it the nuclear force. Some textbooks call it the strong force. Some call it the strong nuclear force. We're just going to kind of call it all. This is kind of reminiscent of London dispersion forces. Some texts call it dispersion, some call it London forces, some call it London dispersion. We just try to do the whole thing so we can capture wherever that term might fall. So that strong nuclear force is what's trying to hold it together. So we have one force that's trying to rip it apart, one that's trying to hold it all together. And that's kind of the battle, if you will, in the nucleus. Jackson wants me and Noah to get along so we can be in the same room together. You don't look very thrilled about this, Jackson. So he's trying to calm us down. He's trying to get in between us. He's trying to say, hey, guys, come back together. We all like baseball. And isn't that what's more important? Because there's probably a lot more people in here that don't like baseball than do like baseball. Heck, I watched this, I think it was Sports Center this morning. There was a baseball player from the White Sox that went on and talked about the fact that the game that he won the Player of the Month for, he's like, yeah, it's kind of a boring game. Oh, man. I don't know. I like baseball. You like baseball, right? You watch it, you play it, so, you know, we have that in common at least. The strong force is an attraction between particles within the nucleus. Now, technically, protons have strong nuclear force as well. However, that's really overshadowed by the fact that there's a lot more repulsion occurring. So usually we refer to it more as the neutrons and the protons in the nucleus all attracted to each other. It's not like a gravity type attraction, and I'll actually get into the next slide of how that attraction occurs. But here's the difficult part about it. Is it only works over short distances. So again, we've established that Noah Dixon and I don't like each other because I like the Brewers and he likes the Cubs. And we've established that Jackson is kind of our middleman. Now, Jackson, you're not a Cardinals fan, are you? Okay, thank goodness, because then we both dislike you, right? Yeah. So then we'd have something common then. A common enemy can bring people together. But no, he doesn't, so that's good. But now, if Dixon is at the other end of the school, I no longer have directly in between me and him the guy that's holding us together. So we need that to be in the short term. So in other words, repulsion acts over a large distance, so the bigger an atom gets, the more repulsion that there is. You need more neutrons to balance that out, because neutrons are more of a short-term fix. to better understand the nuclear force and how something without a charge, a neutron, is able to attract something with a charge, a proton, to kind of hold it all together in a tiny little nucleus, we have to take chemistry a step further than we've done before. And what I mean by that is probably when you were in, I don't know, 6th grade, 5th grade, you learned of a thing called the atom. It's the tiniest thing that makes up stuff. You cut things in half, you cut it in half, and at some point you can't cut it in half anymore if there's an atom. But then probably a year or so after that, or 2 years, you learned that there's things that make up the atom. There's these things called a nucleus, and inside of it there's protons and neutrons, and then there's these electrons that are zipping around. And even at the beginning of this year, 2nd unit in the fall, we talked about where those electrons are located. Remember S, P, D, and F orbitals? We got to take it a step further now. And that step further is we need to talk about something called quarks. Quarks are even smaller yet. So when I say it's a fundamental particle of matter, that means it's what makes up other things. We don't know of anything that makes up a quark. We know what makes up a proton and a neutron, because that's not the smallest thing possible. Just like, again, at some point you thought the atom was the smallest thing possible when you were much younger. But then you learned, no, there's something that makes up that. Well, today we learned that there's something that makes up those things that make up those things that you thought were the smallest things. Catch all that kind of? I really didn't catch it myself. I was just kind of rambling there. Protons and neutrons. We actually don't know if there's something smaller that makes up electrons right now. As far as we know, electron is a small subunit. Protons and neutrons are made up of quarks. And that's where I say it's kind of like a subatomic particle. These quarks can be discovered in particle accelerators. So particle accelerators, and we might show you a little bit about that eventually when we talk about fission and fusion, they start whipping particles around at almost the speed of light, and they crash them into other things. And when that crash occurs, sometimes things can blend together to make a new element. Sometimes things are just going to break apart. And sometimes then we discover these 6 different types of quarks. They were called flavors of quarks. Now, you don't have to know the 6 types of quarks. Although, my slide on the very bottom picture here shows the 6 types of quarks. There's the up quark, the down quark, the top, the bottom. This is the best I can do for strange and charm. Really, you don't have to know those, although the up and the down, these are the 2 things that make up protons and neutrons. A proton is 2 up and 1 down. A neutron is 1 up and 2 down. Again, not that that really matters. That's not a question that we're going to ask you ever. The reason why I'm going over all of this, 2 parts. Again, part of it, I think, is the fact that I think you guys should be aware of the fact that there is actually things that make up the things that we thought make up atoms. So there's smaller things yet. And who knows, maybe someday we'll discover that there's something smaller than quarks that make up that as well. But the reason why I go over this is for my last bullet point on this slide. When an up and 2 down come together to make up a neutron, when they fuse together, there's energy now that is left over. That residual energy of when they came together, that energy is the attraction between 2 particles. When protons have 2 up and 1 down quarks come together, same thing, there's leftover energy. So again, energy has to come from somewhere. Conservation energy law. And it's in the original kind of coming together of quarks to make protons and neutrons that this leftover energy is what holds the nucleus together. That's the strong force. However, if that is not as strong as the repulsion, it's an unstable nucleus. And that's what this unit is going to be about. Is why do things become unstable in the nucleus? That's today's goal. And then the next 2 class periods, how do they become stable? So what mechanism will they use to get back to being stable? Then we go over how long does it take for them to get back to being stable. Okay, I have 2 more slides to go. And the first one is a reminder of this band of stability graph that you saw in the reading guide. And this is actually on the back side of the sheet that we're going to work on when I'm done with notes here in a few minutes. So again, we don't have to try to write this down or anything like that. A reminder from what the reading guide was meant to give you. A nucleus has to have a proper ratio of neutrons to protons to be stable. And as an element gets bigger, it needs more neutrons per proton. Elements early in the periodic table typically have the same number of protons as neutrons. Again, carbon-12, 6 protons, 6 neutrons. But as you go down the periodic table, at some point, you need more neutrons to hold all those repulsive protons together. Now, one of the things to note about this, so far, whatever I've said is that kind of protons bad, neutrons good. If you think about it, protons repel, neutrons hold it all together. If you've ever heard the term or the phrase, too much of a good thing, that applies here as well. You can't have too many neutrons in a nucleus. If so, it's not the right balance. That's why my first bullet point says it's the right ratio of protons to neutrons. This band of stability graph kind of shows us that ratio, where early on, here's element 10 protons. If I hit the band of stability, go over, it has 10 neutrons. It doesn't have 20 neutrons. Again, that would make it unstable. That nucleus would be too big for the number of protons it has. But if you get to like element number 50, and if I climb up the graph, it looks more like a little above 70 is how many neutrons it has. It's no longer a 1-to-1 ratio, because as you get bigger, you need more neutrons to hold it all together. Notice that this graph stops shortly after element 80. But there's well over 100 elements on the periodic table. The reason why this graph stops at that point is at some point you are just too big, which means it doesn't matter how many neutrons you have in the nucleus, you are unstable. Lead is usually considered the breaking point. Any element larger than lead on the periodic table is unstable. You could have 3 neutrons for every 1 proton. It doesn't matter. It is too big at that point. So large atoms are unstable. Remember when we went over the homework, I talked about these elements that are outlined at the bottom of the periodic table. They're all bigger than lead. They last for a split second, and then they're gone. So that berkelium that someone at Berkeley made once upon a time, and hey, now I get to name the element whatever I want to. I would name it after myself personally, but they named it after their university. That berkelium lasts for a split second, and it's gone. It's breaking down into something smaller, a little bit more stable. And what you're going to learn over the next few class periods is that breaking down might take several steps to occur. That sometimes just one thing won't fix the instability. I mean, there might be something that's completely wrong with it and has to go through a lot of steps. The very last thing to remind you of is a term that was on the reading guide as well, called transmutation. One element turns into another element. This occurs in order to achieve stability. I would hope through the course of this year, either myself, Mr. Butters, or Ms. Knatz talked about stability with a lot of different topics. And this is the last time that we hit this, is dealing with the nucleus. if a nucleus is unstable, it's going to drive towards stability somehow. And what that typically means is it's going to turn into a new element. Berkelium will decay down to americium. That'll decay down to neptunium, down to protactinium, down to probably actinium, then francium, then astatine, then bismuth. Then it might get down to lead. So the goal of the notes, because now we're done with the notes, was protons repulsion, neutrons with the protons, strong force holds it together. It's the balance between the two. But we have to have that right balance.